We're on YouTube as well, so I think we can start.
Okay, well, I'll give you the say anyway. So Malcolm Perry will start. Malcolm, you start, right?
I'm trying to start.
Yeah, you have to share your screen, I guess.
I just tried to do that. Didn't seem to work. Let me try again.
So there is an icon, share screen.
Share all participants. So the answer is, should work.
So there's a green button at the bottom of the screen. You have mute, unmute, start video, security, participants, and then share screen.
Yeah, you should. Though I have pressed that, it was green, and you should now see the right thing. But I can't tell whether you're seeing the right thing.
No, we're not seeing.
Who can start when someone else sharing? Okay, so I've just changed it to all participants. Try again.
Well, nobody's sharing, so it should work. But
Let me try again. I'll start. Right.
yes,
That looks good. Oh, well, that doesn't look so great.
It doesn't.
no, we see things very strangely.
It's an SL2C transformation. It's SL2C transformed. Now goes to tau plus 1.
Yeah, there's a shear transform. Okay, maybe.
Yeah, there's some very weird thing. I've never seen this before.
Do we need to restart the stream?
Maybe
Malcolm, if it doesn't
share.
work, I can share my screen with your slides and you tell me when to go to the next one.
That sounds like a good idea.
Malcolm, do you want me to try that?
Yeah, try it.
Oops. Yep. Okay, that works.
That looks good. You can go to the next slide. So I think that the real point about these soft hair and its relationship to black hole microstates comes or starts off really from discovering that there is a gap in the Nohair theorems. Traditionally, one thinks of the Nohair theorems in asymptotically flat space-times as saying that everything is completely characterized by the mass, the angular momentum, electric and magnetic charges of the black hole. By electric and magnetic charges, I mean the monopole charges. That leads to the idea that whatever a stationary black hole is about is characterized only by these four objects, and all black holes are otherwise the same. The difficulty with this classification is it omits the possibility of soft hair. So let's think a little bit about asymptotic charges. In electromagnetism, in flat space, it's easy to see that the past endpoint of Scri plus, you can have an electric field defined at some point on the celestial sphere. Similarly, you can compute the electric field at the future endpoint of Scri minus, and what you discover is that the term that looks like 1 over r squared in the electric field at Scri plus minus is the same thing as the r squared times the electric field at the antipodal point on Scri minus plus. This is known as electromagnetic matching or antipodal matching. It's certainly true in flat space-time, and Christodoulou and Kleinemann have shown that it is true for also the gravitational field and in space-times that are fairly close to Minkowski space. The words fairly close are not quite clear to me, but there is evidence that it's more or less a universal property. Given that, you can find an infinite number of conserved charges simply by taking the moments of the electric field, either at the past endpoint of Scri plus or the future endpoint of Scri minus. and those are the charges written here as Q plus and Q minus. There's going to be, so the real point is that if you consider what happens as you go from the past to the future, there are a set of conservation laws more than just simply the conservation of electric charge. There's going to be conservation of all of these moments. Can we have the next slide, please? So one thing that you can do is to construct a flux formula that tells you how the charge changes as you go up and down scri plus or scri minus, or even to I plus or I minus. That you simply get by applying Gauss's theorem to the previous integral. And what you see are that there are two contributions. The first is dy times star f, f being the electromagnetic field strength 2 form. That's the soft charge. And I guess someone is going to talk a little bit more about soft charges later on, so I won't say too much about that. But the soft charge is essentially due to large gauge transformations which move you between different degenerate vacua of the electromagnetic field. The second term is more obvious. It simply corresponds to the hard charge, the current that flows through scri, or I plus. So you have an idea of how the charges evolve as you move in space-time. As you move up and down scri plus, it's possible for charge to enter the space-time or leave the space-time, and the flux formula tells you how that is happening. If you think about an eternal black hole space-time, the flux formula tells you how things change, but over all of the future or past endpoints of the region that you're considering evolution in. So that if you have an eternal black hole space-time, you'll need to extend the flux formula over all of the horizon, and that will give you some idea of the charges entering or leaving the black hole. You can, for example, implant charges into the black hole, and I guess Andrea is going to say something about that a little bit later on. In evaporating black hole space-times, you have to treat the horizon somewhat differently, largely because the horizon disappears at some point. However, the same idea will apply. There will be fluxes which go through the black hole horizon. This leads to the idea that black holes have soft hair, as well as, so those correspond to charges on the black hole, in the same way that there are charges sitting or going through scri plus or scri minus. Can we have the next slide, please? There is a general method for determining what these charges are. The idea is you start from an action for a collection of fields phi. If you start from the action, you can vary the fields, and that will give you a bulk term which looks like the equations of motion, and a boundary term, theta. There seems to be a misprint on the next line. Obviously, a spell checker has been at work. It should say symplectic form, which you can construct from theta. And I think originally that should say that it's the variation of theta with respect to delta prime minus the same thing the other way around. If you put delta prime phi equal to a gauge transformation, then you'll end up discovering that the symplectic form is the d of something, and that d of something you consider to be the change in charge between phi and phi plus delta phi. The integral to be taken over any closed 2 surface, which is the boundary of the 3 surface on which the symplectic form is defined. So that really tells you what the charges are. You can do this kind of construction for the electromagnetic field and reproduce the charges that we just had earlier, or you can do it for the gravitational field, in which case you'll find at infinity supertranslation charges and superrotation charges. If you did it on the horizon, you would find a collection of softer charges. Can we have the next slide, please? In general relativity, you expect charges to obey, since G is a coordinate transformation, you expect the charges to obey the algebra given there, which tells you the Dirac bracket of two charges should be the charge of the Lie bracket of the two diffeomorphisms, with possibly a central term, which at some level represents an anomaly in the diffeomorphism algebra. That anomaly must be cancelled by something. Can we have the next slide, please? You can do some simple calculations in the Kerr spacetime or in Kerr-Newman, or for that matter, ADS Kerr, and you'll discover that there are two commuting sets of vector fields that define diffeomorphisms on the horizon, each of whose algebra is the Virasoro algebra. The central charge for these algebras in both cases is 12J, and where J is the angular momentum of the black hole. You can also associate temperatures, which are the Frolov-Thorne temperatures, to the left and right degrees of freedom on the horizon. And the general formula for that is R plus or minus R minus over 4 pi A, where R plus and R minus the locations of the inner and outer horizons, and A is the rotation coefficient, J over M.
Sorry to interrupt. Is this just in 4 dimensions or in every dimension?
This is only in 4 dimensions, although we have some evidence that the same kind of thing works in dimension 5. There are difficulties with dimension 6 and up, which have not yet been resolved. Maria Rodriguez and I will produce a paper on that shortly. If one then uses the Cardi formula, one discovers that the entropy associated with the central charge, assuming that these define conformal field theories on sections of the horizon, you discover the entropy of this is 1/4 of the area of the event horizon, which is exactly what you'd expect from the Hawking formula. So what you do is you interpret these as edge states to cancel the anomaly in the diffeomorphism charge algebra. So on sections of the horizon, this gives rise to 2 commuting CFTs, giving the degrees of freedom that define the Hawking entropy. Can we have the next slide, please? The trouble with all of this is it's not really a solution to the information paradox. It seems to me that it's a step on the way to understanding what is going on, but some of the missing ingredients we just catalogue here. The first is that if this is to really describe a way of solving the information paradox, it must be the case that all of the charges have got to classify the incoming and outgoing quantum states. That is to say, that if you know what the charges are, you know what the quantum state that was gave rise to the black hole, or alternatively, if you knew the charges at infinity, that would correspond to knowing all of what gave rise to the original collapse. And then you could say from the fact that the charges are conserved, that it would give rise to correlations found in the outgoing Hawking radiation. But there are obvious problems with this. The first is it seems strange because of the species problem. The Hawking entropy is independent of the spectrum of elementary particles, but the number of ways of forming a black hole surely depends on what the spectrum of elementary particles actually is. If you had 1,000,000 times more elementary particles, you'd expect the entropy to be correspondingly bigger. Another problem is that the Hawking radiation appears to be independent of the charges on the horizon, and I think Jeffrey might be saying something a bit more about this later. So we don't really know how Hawking radiation can encode the origin of the black hole. Perhaps it's just simply holography at infinity, but it's not quite clear. If it's to record information on the horizon, it would appear to contradict the low cloning theorem, because stuff flowing through the horizon presumably just keeps going. Leaving a copy on the horizon would seem a bit strange, although a proof of the no cloning theorem does require locality. And a classical space-time picture appears to be hopelessly inadequate to describe what is going on. First of all, the end point of any horizon, if the black hole completely evaporates, is going to be singular. It's hard to see how causality could be maintained, especially in the case of Kerr black holes. And so ultimately it would seem that soft hair would be part of could well be part of the solution, but is certainly not all of it. So I think that's the place to stop. Thank you.
So please, Andre.
Yeah, should we just continue or should we let people ask questions?
Well, I guess if somebody has a comment specific to what Malcolm
I think it's probably better to continue and then we'll just start the discussion.
So let's go ahead.
Okay, so then Jeffrey and I will just continue and give each some comments on soft hair, and then we'll open up the discussion to more general uses of BMS. So what I'm gonna focus on is some comments on the dynamical mechanism by which soft hair has been argued to be implanted on black holes. And this is related to some topics in gravitational physics at very low energies that have received a lot of attention in recent years. And these are a connection between asymptotic symmetries, memory effects, and soft theorems. And we'll come back to that later when we open up the discussion to other applications of BMS. But for now, let me focus on this dynamical mechanism. Let's start with your favorite black hole geometry. Let's take a Schwarzschild black hole whose horizon is at 2m. If we add a shock wave, this is a gravitational shock wave. This is described by a stress tensor, which I've written here as a monopole term and then angular profile. To preserve the conservation equations, this means we also have to turn on subleading components, in particular, a component that breaks the spherical symmetry. Now, what has been argued that such a shock wave that has such an angular subleading profile can implant soft hair on the black hole horizon. Let's see how that works. So it has been, so this shock wave perturbation as a function of this angular profile T can be shown to change the black hole metric by these blue terms, which are given in terms of this function f, which is a function of the angles, and it's related to T, this profile T in this fashion. Now, what that does is that it changes the horizon radius by some angle-dependent function. And this has been argued to be achievable by the action of BMS supertranslations. So the way that that works is that if you act with BMS supertranslation at past null infinity, which is given in terms of these diffeomorphism vector fields, and you choose this diffeomorphism vector field to be characterized by the same function f that I've shown on the previous slide, then such an action, because you have gauge fixed your solution in a certain way, can have as the effect that the horizon that the radius of the Schwarzschild black hole is modified in this angle-dependent fashion as a function of this parameter f. Now, supertranslation at past null infinity turn on soft charges, as Malcolm already mentioned. In this case, supertranslation at past null infinity turn on superrotation charge, and this is given in terms of this function f by an integral over past null infinity. Now, this is an asymptotic action at the past null infinity that does something to the horizon. You might wonder whether you can rephrase this in a more local fashion by something that happens at the horizon that an observer hovering outside the horizon might describe. And this is indeed the case. So what you can show is that supertranslation at past null infinity can be recast as certain symmetry transformations at the horizon. So this change of the horizon metric by this angle-dependent function can be undone in some sense by acting at the horizon with supertranslations as well as superrotations. And so the relation between the action of asymptotic symmetries as past null infinity and at the future horizon is that supertranslations at past null infinity become supertranslations at the future horizon, while supertranslation at past null infinity also turn on superrotations at the future horizon. So this was just some comments on how the dynamical process of encoding BMS supertranslations and soft hair can be realized. The physical process of sending in a shockwave that carries BMS supertranslation charge, or in other words, displacement memory, gets imprinted in the horizon, and you might call this a black hole memory effect. And it relates the action of asymptotic symmetries at past null infinity to the action of asymptotic symmetries at the horizon. Now, this raises several questions. For example, in this picture, you view the horizon as some sort of boundary that retains a memory of what falls in. There has been some gauge fixing in order to find solutions. There is some ambiguity in defining soft charges in general, which I think Jeffrey will talk about, and I might come back to that later on, which has to do with the fact that there's an ambiguity in defining the conserved integrated soft charges. And then moreover, you might ask, well, this is a dynamical process that encodes some symmetry transformation at infinity into symmetry transformations at the horizon. But how much information is actually stored in this soft hair that gets implanted? And as Malcolm already mentioned, at this point, it does not seem to be enough to address the entropy problem or the information paradox. And there are several more open questions, which I will let Jeffrey comment on now.
Thanks. So let me share my screen too. Sorry, technical. Could you see the screen? Could you see the screen?
Yep.
Yes, it's good that way. Go ahead.
Okay. So so as far as I understand, the soft proposal requires to store black hole information in vacuum states. So it looks to me like that it requires a map from vacuum states to finite energy states to be able to store all the information of the black hole. So please correct me later on, Malcolm, if it's not what is meant. But it seems to me very hard to store so much information without energy. So let's try to see what how would this super translation with the vacua work. So this is my understanding of it. So let's consider null shell, 4-dimensional asymptotically flat spacetime collapsing and forming a black hole, which is then evaporating. So at past null infinity, the null shell leads to a transition between an initial Minkowski vacuum. So Andrea just reviewed this, and a final Minkowski vacuum, and they differ by super translation shift. So the shift by itself is diffeomorphism invariant. So because it's encoded in the Weyl tensor, it is sourced by the leading order stress energy tensor of the null shell at large radius. So it's sourced by classical piece of the matter. So particularly the subleading component of the stress tensor of the null shell are not relevant for describing the vacuum transition. So this displacement memory is not sourced by the subleading multipolar structure of the shell. It seems that this mechanism alone cannot encode the subleading information on the black hole multiple structure, and therefore cannot be used to describe the final black hole entropy, because there's a lot of more information that is not used to source this memory effect and this vacuum transition. So let me just try to expand a bit the discussion here, because I think it's part of the topic as well, is to, contrary to ADS, where the boundary data is just the boundary metric and the stress tensor. In asymptotic flat spacetimes, the boundary data at null infinity is a lot of fields. So there is a bonding mass and bonding angular momentum in bounding gauge, but there are also an infinite number of fields in the subleading components of the boundary metric, boundary two sphere metric. And another way to say it is in the Donder gauge or harmonic gauge, where there is an infinite number of multiple moments, so the so-called canonical mass and angular momentum or current multiple moments. So here's a linearized metric, but there are non-linear corrections, of course. So among this infinite number of multiples, so the leading order radiation multiple solves the displacement memory effect associated with BMS supertranslations. So it seems to be an argument that there is no map between vacuum states and finite energy states with these vacuum such defined with each supertranslations. And maybe, and that we can discuss, a related statement might be that soft theorems only provide a limited amount of information on amplitudes. One cannot deduce amplitudes just from their soft limits. So maybe we can debate that. So just to mention the bigger picture here, so there's this triangle, this infrared triangle that is Andrea reviewed. There are subleading things happening as well, but it's really overleading and subleading. So once look at not asymptotic symmetries, but really at overleading transformation that would not be usually considered. They are interesting because they lead to nodal charges that are very subleading and that capture the very subleading piece of your fields, which are these independent fields. And they are also associated with different subleading memories, like the spin and center of mass memory. One comment also on horizon diffeomorphisms. So this puzzles me a lot, these horizon diffeomorphisms. So in general, the horizon is a dynamical place, and so it's fluctuating a leading order. So it's very hard to define boundary conditions. In particular, horizon and an arbitrary null upper surface are very similar locally. So it's not clear to me how one could define boundary conditions in general in a horizon. I understand that for killing horizon it's possible, at least at linear level, because there is a background structure. But I would like also to point out that there are various ambiguities in these such constructions, like already in KRCFT, like for extremal case, extremal Kerr, one can design an ansatz for a Virasoro asymptotic King vector, where the central charge depends on the ansatz. So there is a parameter B one can introduce, and it shows up in the central charge. And there are also boundary terms in the symplectic structure that one could add that would also modify the central charge. So all this has to be a bit discussed to see how unique the construction can be and what are the definite results one can establish this way. And then the final comment, so on soft dressing. So as Malcolm already announced, that so the soft emission factors out of the S matrix in a fixed spectral background. So that's a result by these authors. And Hawking emission therefore not affected by soft dressing. And that was obtained using Fadeev-Kulish formalism, using dressing with soft cloud photons. And so we obtain also similar results using a different technique, using quantum field theory in the curved background where you have a shock wave, and such shock wave induces a transition, supertranslation transition, and we computed the Unruh radiation in that background and parallel this to Hawking emission, and we found similar formula, with also showing that there is no effect. So we'll close this. There is extra topics for discussion for later on.
Okay, so maybe we should let the audience have, if somebody in the audience has a comment or a question.
Yeah, so I was wondering if someone could comment on the relation between, if any, between this sort of soft hair and the affine Virasoro algebra that's encountered in ADS3. In particular, in relation to Jeffrey's comments, I believe there were computations by Steve Carlip trying to use a Virasoro algebra defined at the ADS3 horizon in order to count black hole entropy. And he ended up with, I think, a very similar issue that he could get any central charge he wanted for that Virasoro algebra just by choosing different Virasoro subalgebras of three-dimensional diffeomorphisms near the horizon. So anyway, just as a general question, is there a relation or is there an application of the formalism that's been developed for BMS charges and a relation of that to things that we know well about ADS3 CFT2?
So maybe I can give some elements of answer. So well, BMS has been mainly developed for asymptotic flat spacetimes and around the horizon, so not directly for ADS3, but indeed it's related for the horizon. For finding boundary condition on the horizon, it has been attempted by Carlip and many authors afterwards. There were always issues with these constructions with the choices of boundary conditions and boundary terms that is related to the boundary conditions that one should add and to define the dynamics. And there are also issues to define the temperature uniquely, because typically the normalization of the vector once defined in Virasoro algebra will affect the value of the temperature. So one needs an extra argument for fixing it. So in the case of horizon, since they are, well, in the extremal limit, there are independent ways to define a left temperature using the geometry of the near horizon geometry. So there are arguments to also fix temperature that way from the extremal limit. But it seems to me that there's never been like a complete answer for these constructions in terms of managing all the possible terms one can add, all the ansatzes one can add, all the boundary terms one can add to have a unique, to prove that it's a unique answer. So I don't know if... Maybe Malcolm wants to add.
Malcolm, your microphone.
Go.
We can hear you.
Can you hear me?
Yes.
I can say a little bit about what happens, the relationship between 4 dimensions and ADS3. So the near horizon geometry of Kerr is vaguely similar to what happens in ADS3. So what you can do is you can describe the near horizon geometry as a warped version of part of ADS3 times a line element, the line element corresponding to the latitude you are on the black hole horizon. So the ADS3 type of geometry corresponds to phi, r, and t in the usual Boyer-Lindquist type coordinates. But it's not all of ADS3, it's ADS3 quotiented by something, and the something is controlled by the fact that the azimuthal angle phi is identified with period 2 pi. That gives rise to the identification of 2 of the coordinates with periods which correspond to the Thorne-Frolov temperatures T left and T right. So in that sense, the temperatures are not ambiguous. There is a potential problem with the central charge, which I didn't really discuss, and that is that you have to make sure that your charges that you have are integrable, and in as much that there is a weak spot in the argument, it is making sure that the charges are integrable, and the fact that the result of that gives rise to the central charge of 12J. I think that if we're to be completely honest, that has not been completely nailed for sure, but since the same techniques work for Kerr ADS and don't give rise to any ambiguities, there doesn't really seem to be a problem. I don't think I have anything else to say on the subject.
So Malcolm, this is related to these Wald-Zupas counter terms that you have to add.
Exactly, yes. So the question of whether or not the charges are integrable, what one would have to do is to define precisely what the charges are and then find what you have got to do to make the Wald-Zupas thing work. What we in fact did was to make a guess, but the interesting thing is the same guess works for Kerr ADS, which is vastly more complicated. So what that means is that it is plausible that this is the right thing to have done, but a sort of real proof that we'd found the right Wald-Zupas type term is currently still a little bit missing.
So is it any other question?
Yeah, so just add, maybe I just give questions, but or ask.
Wanted to follow up a little bit on the. I'm getting terrible echo here. Oh, I've muted
I think that's
Malcolm.
because you're using headphones. You are using two things at the same time. So if you just don't, I mean.
No, I've muted Malcolm, and it all works fine now.
Ah, so Malcolm is the problem.
Malcolm is the problem. I've got an echo from Malcolm. Anyway, so
we cannot hear you, Malcolm.
I'm gonna just ask Malcolm a question. Following up on Emil's question, there's a beautiful ADS3 CFT that we know in the D1, D5 system. If you applied all this machinery to that system, would you start seeing details, or what would be the charges in that D1, D5 CFT? What would you learn about the D1, D5 CFT by applying this machinery? I'll unmute you.
Well, I think the answer is that we haven't tried, so I don't really know.
If I can maybe try to provide one answer. So I would slightly agree with Malcolm saying this ADS3 is more like ADS2, like Joseph was also saying earlier. You cannot put any finite energy excitation in these near horizons without destroying the near horizon and back reacting. So in a sense, there's no well, there shouldn't be a CFT by itself. There should be like a CFT coupled with some exterior, which is the exterior of the black hole. So because any energy that enters close to the horizon changes the horizon at leading order, and therefore it's more like a CFT coupled to another system. So it's a mixed, it's an open system. So intrinsically there are no conserved, well, no conserved charge. There are just charges that flow, and that means there is always a flux of energy through the horizon.
If you want to say something, Malcolm, you have to unmute yourself. Yeah.
He's muted himself.
No, you did it twice. Yeah.
Okay. I should say that I agree with what Jeffrey says, but also since there is flux across the horizon, it ought to be the case that there is some kind of three-dimensional theory which tells you how the horizon behaves and how the horizon evolves, rather than just looking at two-dimensional sections of the horizon. So I agree that there must be more to it, but I'm not really in a position to say what that extra stuff could be at the moment.
Andrea, have you comments?
Well, I agree with what has been said. I think maybe one should think of these charges as a snapshot, but then, I mean, over time, the system evolves and the soft hair will hopefully dynamically evolve. We also know that from when finite energy wave packets across the horizon wiggles and then settles down, and there should be some dynamical picture of these soft charges evolving, perhaps.
Yeah.
So I've got a very naive question. How do the soft charges actually influence the Hawking process? Look, a very stupid question. I mean, Malcolm started out by saying that the uniqueness theorems have a hole in them. So what does it tell me about the near horizon metric, and how does that near horizon metric feed back into the Hawking process and bring the information out of the black hole?
Well,
Nick, that's precisely the question, right? So the dynamics we don't know yet, and but Jeffrey made some comments about that the soft sector does not affect Hawking, the Hawking radiation.
I appreciated that comment, but at least it should tell me how it modifies the metric near the black hole, or how the local environment in which Hawking did the calculation is now changed. Maybe you can't do the dynamical back reaction, but I would like to know how any quanta that forms to the surface of the black hole knows anything about the difference in soft charges.
So maybe I won't always answer the question, but I don't know if Malcolm would agree with that. But for me, you know, this, if you look at the infrared structure, if you look at this soft hair in the sense of supertranslation shift, what it really means is that there is a non-sphericity at leading order in a matter field that generated this black hole. So you have a shock wave that leading order has a non-sphericity in it. And so that's the mechanism that generates a soft transition at infinity, at null. So that's, the shock wave is something classical. You can compute the difference of charge between the initial and final state classically. You can say the initial charge was 0, and therefore, the final charge is some non-trivial charge. But the transition itself is classical. So that's what is the soft transition is this leading order non-sphericity of collapse. And as Hawking showed, it does not affect the Hawking solution. That would be my answer.
Can you repeat the last sentence?
In Hawking's paper, he showed, he explained without putting any formula that the leading non-sphericity of collapse would not affect the radiation. I guess he computed the Bogoliubov coefficient in that case. So we just recomputed them as well to check, and it's indeed, and that's the mechanism that introduces a soft transition as seen from the infrared structure.
This is Samir. Can I ask a brief question?
Of course.
So it's an embarrassingly naive question, but maybe it's just asking what Nick was just asking in a slightly different way. Suppose I make a black hole at the LHC of 1,000 Planck masses by some local collision of two high energy protons, and then it just decays, and I collect the decay products, and I check what the scattering matrix is. Now, this entire thing, of making the black hole and seeing how the whole radiation comes out in a time of order m cube, it all finishes off in a spatial distance of less than a centimeter, because that's how far the quanta would go in that much time. So why would how the things behave at infinity ever be relevant to the dynamics of what happens, which I can do all just within the LHC? It's a very naive question, so I'm sure I'm missing something here, but maybe I could just add a second part to the question. It seemed to me that if you look at diffeomorphisms of a space and look at boundary degrees of freedom, I'm a little puzzled about what they mean. Like if I take a big piece of paper and I say, okay, I'll cut out the boundary at, let's say, 1 meter square in my coordinates, and then you slightly change the coordinate and say, again, I'll cut it out at, x equals 1 meter in the new coordinates. I get a little bit extra piece of paper at the edges, maybe lose it somewhere else, and I could say, okay, I have changed something about the state. Is this all that I end up doing when I'm looking for boundary degrees of freedom? And if so, how can I change something which is happening in the middle of the piece of paper where, I collide two protons, make a black hole, 1,000 Planck masses, collect, 10 to the 6 quanta, and they go out about a centimeter. And, I've already seen everything there is to see. So somehow I'm a little puzzled between the degrees of freedom at infinity, what they mean, how they could mean something, and why they could tell me something about the information puzzle. Just that was the question. It's very naive, and I apologize for that.
Maybe I can just give one sentence. Then, so the Hamiltonian is a boundary term in gravity. So it's really a boundary term. This is the only theory where this is the case. So anything that happens inside is known at the boundary, I would say. But that's the only thing I want to say. Maybe.
Andrea, you wanted to say something?
Yeah, so this is what I mentioned before about, so once you fix a gauge, for example, typically in literature, Bondi gauge is fixed, which sets GRR and GR and the angle coordinates to 0. Then if you act with the BMS supertranslation at non-infinity, that tells you how the metric has changed in the interior. And that's why you can say that the horizon has now this angle-dependent shift.
So maybe I could just ask, it was Jeffrey was saying a second ago, it's true that if you integrate the on-shell value of the Hamiltonian, it's a boundary term. But when you want to actually do evolution with the Hamiltonian, you want to take a Poisson bracket, you fix a gauge and you do evolution. Degrees of freedom inside actually matter. I mean, if you have, let's say, 2D gravity coupled to a scalar field, you actually have to do the Poisson bracket of, the Gij and the Πij all the way inside. Knowing the value of the Hamiltonian is not enough to actually get you the evolution. It's the Poisson bracket with the value, the changes of the Hamiltonian, of the canonical variables, which actually give you the evolution. So I know people often say the Hamiltonian is at the boundary. I haven't ever understood what that actually means in operational terms. I mean, can you really see all that is happening at the boundary by somehow that is happening inside by just looking at the boundary. Could you quantify what that means a little more accurately?
Sorry. Could I jump in here? Or?
Ah, yeah, it's perfect. Yeah, please answer
Yeah,
this. It's perfect.
I think I think the answer is yes, Samir, and you can do this in perturbation theory. We can ask the following kind of question. You see, let's have a shock wave that comes and hits null infinity at somewhere in the middle of null infinity, which is say u equal to 0. Okay, and then the question is, I am sitting near the past boundary of future null infinity, and I want to know what was the shape of the shock wave. And the answer is you can do that explicitly in perturbation theory. And the protocol to do that is, you need to act with the unitary, which I can tell you, and then you need to measure the Hamiltonian and determine the probability that you're in the vacuum. So that's like a measurement of P0. And you can write down a formula that tells you that because the Hamiltonian is a boundary term, you can determine what's going on inside. I mean, I don't know if that was very clear, but one trivial example where it would work is, if you just measured what was going on outside and found it was 0, you would know the nature of the space-time everywhere. You would know it was vacuum everywhere. And in more complicated cases, you need to do more complicated measurements, but you can literally quantify and determine what's going on inside from near the boundary. I mean, you could write down formulas that would tell you what the state in the interior is. So it is really a physical thing.
So sometimes people say that you could maybe, for example, measure the energy at infinity, and so that will tell you what the state is as long as there's no degeneracy of states in the interior. It's very interesting to me, however, that in fact the whole Hawking puzzle, when you make a horizon and you keep a semi-classical metric inside that horizon, actually exactly creates the degeneracy which you are trying to avoid there. Because once you have a horizon and you can make both positive and negative energy states on a complete space-like slice, the number of states at any given energy actually immediately becomes unbounded. That's just another way of phrasing the fact that once you have negative energy quanta and positive energy quanta, you don't have a finite number of states and the energy gap is 0. I've always just been curious. I would like to see some way of making a concrete, maybe discretized model of a space-like slice, Gij, Pi-ij variables everywhere, and then people trying to show me how from the boundary you see the inside. I just haven't seen it clearly enough, and I would like to see that.
The claim is not, just to be clear, the claim is not that if you only measure the Hamiltonian, you find all information. The claim is you need to measure the Hamiltonian and other operators near the boundary. So of course there could be degeneracies. You could take two scalar fields and let's say we allow global symmetries. They could be related by some global symmetry, and you might have degeneracies in the energy. But if you also allow me to measure other operators near the boundary, you can explicitly determine what the state in the interior is. But I mean, we try to write down formulas of this kind. I think you can make it quite explicit in many cases. So just to clarify, it's not only the Hamiltonian, but it does take advantage of the fact that you have the Hamiltonian, which is a boundary term.
Sorry, is what you are saying, Subrat, that you can just evolve backwards in time and find what the what the shell was? I mean, if you have the Hamiltonian, you can do that and find what you sent.
It's related to that, but I was trying to give a more physical protocol because evolving backwards in time is a very complicated thing.
Well, so but that might be simpler. In many cases, evolving in time is relatively simple. Like in all these discussions of complexity that Lenny has and so on, evolving backwards in time is a relatively simple operation.
Yeah, I mean, okay, you could put it that way. I was thinking in terms. I mean, I always like to think in terms of measuring the projector on the vacuum, which I think is easier to do. But you could think in terms of what you just said as well.
So I guess we should come back more to the subject of asymptotic symmetry slightly. So Malcolm and Andrea, would you like to comment on the criticism that Jeffrey did on the possibility that the problem could be resolved with soft-hair state?
If you were careful, I had said on my slide that this is not a solution to the information paradox, at least not yet in this current form. So
you are happy with the criticism of Jeffrey?
I would too.
Malcolm?
Well, I'm in agreement. There must be more to it, and this would appear to be an approach which gives you some new ideas, but it is certainly not the answer.
maybe let me make another comment. So because we talked about this relation between asymptotic symmetries and memory effects and soft theorems. So, I mean, these things are related to other properties and other topics in other fields of, let's say, very low energy physics. For example, in the asymptotic symmetry and the construction of soft charges, there are these ambiguities. In particular, if you choose boundary conditions that are not strong enough, the asymptotic charges generally will be divergent, and you have to come up with a renormalization procedure, which Jeffrey can tell you all about. And then even if you have fixed your divergences and you get a finite charge, there's still a remaining ambiguity, and this you can fix in some cases that have been studied by demanding equivalence with corresponding soft theorems that are supposed to be equal to that. So there's a lot of ambiguities or things that are not so clear, and hopefully with these other connections to these other aspects of infrared physics, some of these can be fixed in some way, but it would be good to have an independent understanding of those, independent, better understanding of those. And I think there's still a long way to go to resolve all these issues. Yeah.
Can I jump in with a question, which is mostly for Andrea, but also for the rest of the panel? So it's to do with the LLM system in ADS5, looking at the half BPS sector. So there was some work done in late 2018 by Balasubramanian, Berenstein, Lukovic, Parakar, and a couple of other people, trying to make a link between the soft hair modes and the description of those half BPS LLM geometries as being microstates of a zero-size singular incipient black hole. And so their picture was that if you do a coarse graining, you can see an emergent infrared soft mode arising from the UV description of the microstates. It wasn't there in the UV description, but it emerges at low energies. And it seems to have the same kind of flavor as some of this discussion of soft modes. So my question is, what's your updated understanding? I know we discussed this at pre-strings last summer. So what's your understanding of this relation, and can it be done in other situations, perhaps?
Andrea?
So it's for Andrea.
Yes, I'm not sure what to answer to this because I don't really have an answer of an updated understanding of what happens in other situations. I remember what they talked about, and the reason this the soft mode appeared in this LLM geometries was by demanding regularity of the solution near the place where the horizon would be. But I don't know what you want me to comment on.
Just that it seems like a link between what we heard about earlier in the day and what we're hearing about in this session, that this soft mode...
It has a similar flavor, yeah, but I don't have any updated
because I think at the time the understanding was that there is a coarse graining procedure which produces something which looks like a soft mode, which would describe some IR motion within the space of the microstates which are understood in the LLM solutions. But it seemed like it hadn't quite been made precise that it was really exactly the same soft hair modes that are being discussed in this session. So it would be nice to see how precise that connection could be made.
Well, the soft hair that we're talking about in this setup is in four-dimensional asymptotically flat space, while in the LLM situation, you're in ADS5 cross S5. So I mean, it's not exactly the same situation, but it's a low energy mode that they are talking about.
Okay, thanks.
Well, isn't it the case that you want to go the other way? That is to say, you want to know what the soft mode tells you about the microstates rather than the other way around.
Well, I think both ways will be interesting. So, if one can understand the soft modes as describing a subset of IR dynamics of some Hilbert space of microstates, which can in principle be described explicitly in string theory, then I think both can inform each other.
Mm-hmm. Sounds promising.
But do you have an answer to that question, Malcolm, one way or the other?
No, I have no answer to that, but I think the idea sounds promising.
Is there a question or comment? Yeah.
I have a question for Jeffrey.
Yes, please.
Jeffrey, a question is as follows. Actually, you mentioned something about amplitudes and being fixed by soft factors. So I wanted to ask the following question. Let's say I give you I have some configuration of hard particles, and then I tell you what the soft factors are for emission of any number of gravitons in any direction. So I'll tell you the soft factor for 1 graviton in all possible directions, and then for 2 gravitons and 3 gravitons and so on. How well can you reconstruct the original amplitude if I gave you all of those soft factors? Has that been quantified?
I remember I saw a talk on this where the speaker was trying to argue he could reconstruct the entire amplitude, and then it didn't happen well. Well, he was making a lot of hypotheses on what is in the amplitude and what.
Like rational amplitude or something like that.
Yeah, it was exactly. It was rational first, and then it was there was a limitation on the polynomial order on each numerator, denominator. And I mean, if you don't know it's rational, and I mean, then you have too many possibilities. You just cannot reconstruct it. So I don't know how much information, but I would say not all information. You need extra data.
I see.
But I can quantify it.
Maybe I could rephrase that question in the following way. I mean, for instance, let's say we were in ADS3 and I told you all the Virasoro charges. I would still not have completely specified the state, because you might have multiple copies of a certain representation. So at most, if I told you Virasoro charges and also products of Virasoro charges, everything in the enveloping algebra, I would be able to specify which representation I was in and which state within the representation, but not, if I had multiple copies, I would not be able to differentiate between them. So what is the analogous statement for the BMS group? I mean, do we understand if we take some configuration of massive particles, if we could have degenerate representations of this kind? This is a rephrasing of the previous question, because all these soft limits will effectively give you all the supertranslation charges.
Well, I don't think I can really answer that question, but I can answer at least that if you take a multiple soft limit, you know, the way you take the multiple soft limit, it's related to the BMS algebra. So you can relate the commutator of the BMS algebra with the double soft. So you can find part of the representation theory of BMS in these soft double soft amplitudes. But no, really, I don't know. I don't think that your program has been done. I mean, for the Virasoros, it has probably been done much more than for the BMS case. Maybe Andrea has more thoughts on amplitudes.
No, not really. I can tell you about the conformal soft version, but I mean, those are, I mean, the soft terms are universal factorization properties of amplitudes when the energy of external masses particles is taken to 0, and then they constrain some amplitudes, but they're not enough to fix all kinds of amplitudes. I mean, they fix some low point amplitudes. They're helpful to constrain the properties in the structure.
You also mentioned that I think there is still some more soft knowledge to be found on these amplitudes, because in the CITER there are these adiabatic modes, so-called adiabatic modes, and there are also infinite number of wild identities related to these adiabatic modes. Somehow there's an analog in flat space of this. Where here there was a leading and subleading and sub-subleading graviton. And I think that there should be a version of sub-n leading, but with some kind of projector that should involve, so there should be some algebraic relations there in subleading orders.
But if I may ask, the n sub, isn't it something of the 3 amplitude that is not meant to go beyond in the quantum amplitude, whereas the leading has to be there?
Could you repeat that? Sorry.
Is it that you expect to really have sub leading universal structure also for quantum amplitude? Because I expected that only the leading and maybe the sub leading by just following by Lorentz invariance of the distribution has to be universal, but the rest would be generically modified.
No, you're right. So yeah, I was thinking classically. Yeah, yeah. I don't know so much about the various breaking of the quantum corrections.
But maybe there's some experts in the audience who have worked on all kinds of soft theorems and amplitudes that want to chime in.
So I could try and jump in a little bit. So it's true that you might have sub leading soft factors, but as Jeffrey pointed out, there'll be some projectors involved, and so the sub leading soft factors will have one piece that's universal, and then the rest of it will depend on the details of the theory. And the piece that's universal you can extract it by using a projector, and that's the part I think that you can associate it to these infinitely many adiabatic Ward identities that Jeffrey was talking about. And I think you can take this to all orders. Another comment I wanted to make was about related to these soft theorems. If you try and ask what the asymptotic symmetries are associated to these subleading soft theorems, they're often associated to some transformations on the phase space which are divergent, which take you out of the phase space because they violate the boundary conditions that you're imposing. And it's often been the case that we try not to talk about them, but I like to point out perhaps a different point of view is that we should allow for transformations on the phase space which have divergent charges, but still have finite Ward identities. This is, for example, what you might expect if you have spontaneously broken symmetries, because you can't write down charges for spontaneously broken symmetries because they have divergent action on the phase space, but you still have finite Ward identities. So this is, for instance, what happens with subleading soft photon theorem as an example, where the transformations for this is well known, but they take you out of the finite energy phase space. So you don't have finite charges, but you actually end up having a finite Ward identity, and it's associated precisely to the subleading soft theorem. And the same thing is true for the subleading soft graviton theorem as well. So I just wanted to add that as a comment.
If I may ask, are you talking about the Lorentz-Virasoro generator?
I'm not talking about the Lorentz-Virasoro. I'm talking about the subleading one, which is a totally different symmetry. But on that, I'll also mention if you take this viewpoint, you can now start asking questions about higher dimensions. So one of the confusions is that in higher dimensions, you still have the soft theorems. Soft theorems is a dimension-independent concept, but you don't have the Virasoro anymore. The Virasoro is a very special property of just the 4-dimensional or 4D gravity. But if, on the other hand, you start allowing for arbitrary diffeomorphisms in higher dimensions, now again, arbitrary diffeomorphisms will not preserve the phase space. They'll take you out of the phase space, but you still end up having finite Ward identities. And those finite Ward identities give you precisely the subleading soft graviton theorem. So I think the picture is that you start off with the theory, the boundary theory, whatever, quote unquote, whatever that is, has the full diffeomorphisms as a symmetry and everything except for the global conformal symmetry is spontaneously broken. You can write down Ward identities for the ones that are spontaneously broken, and you end up getting the subleading soft graviton theorems. So then you don't really have any issues even with higher dimensional the asymptotic symmetry interpretations of higher dimensional soft theorems.
I just totally agree with you. Just to mention, yeah, I think that's the case. I mean, you can even make it even stronger and say that if you have all these overleading transformations, because you always have two ways to think about this. You can, when you have these noted charges associated to these overleading transformations or very, very subleading transformations, either these charges are 0 or they are infinite, but you can actually, yeah, if you take the infinite point of view, You can even normalize things and make it finite and have finite variable entities. There is a construction for putting them finite. And I agree that it goes to higher dimensions as well. If you go from the Virasoro's in 4D to diff S2, which is what seems to be required anyway for the subleadings of graviton theorem. This is the natural thing, actually, also from the point of view of classical gravity, because the associated charges are the Bondi mass, Bondi angular momentum aspect. And the Bondi angular momentum aspect is an arbitrary function on the sphere. So it's natural to have associated to it a generator, which is also an arbitrary function on the sphere. Then you have a one-to-one map between the generator and the charge.
Maybe I expand a bit on this discussion and add some flavor from a purely holographic viewpoint to the extension of the Lorentz symmetry to include angle-dependent superrotations and boosts. Maybe let me just, because we were going to open up the discussion more general, and we had some slides on that. So I don't know if this is visible. But so yeah, so the discussion was about allowing symmetry transformations that change the fields at leading order and lead to divergent soft charges. And this is the case if you allow for arbitrary diffeomorphisms on the celestial sphere as an extension of the Lorentz group, which now includes angle-dependent rotations boosts that come from a vector field that's a general arbitrary function of the angles. In the literature previously, it has been proposed that this could be the proper asymptotic symmetry group of Einstein gravity at null infinity. But it had this feature that it leads to a divergent charge, and Jeffrey and collaborators were able to renormalize that. And once you impose equivalence with the water density of that symmetry, once you impose equivalence of that with the subleading soft theorem, then you can fix residual ambiguity, which amounts to subtracting certain boundary terms. Now, the Virasoro superrotation symmetry that has been discussed in the literature and which gives rise to a 2D stress tensor for 4D gravity is a symmetry that comes with a holomorphic vector field. And you would think that such a vector field might not lead to divergent soft charges, but this is in fact the case too, because at isolated points on the celestial sphere, the metric of the celestial sphere is also divergent, but from a sort of holographic viewpoint, you can actually relate this Virasoro superrotation symmetry, which has a holomorphic vector field, to more arbitrary diffeomorphisms on the celestial sphere, and the conserved charges in this case, after renormalization and after subtracting this residual counter term ambiguity by equivalating it with the subleading soft theorem, are just the stress tensor, 2D stress tensor, and what's known as the shadow transform, 2D shadow transform of it. And you can understand these symmetries from the viewpoint of a conformal basis for scattering amplitudes, where the energy and the momentum and the helicity are now replaced by locations where you insert operators on the celestial sphere, and the quantum numbers under the global conformal group, which are the conformal dimension and the spin. And then you can understand the Virasoro superrotation symmetry and these diffeomorphisms, more general diffeomorphisms from some particular graviton modes in this conformal basis of a particular conformal dimension. And so then from this perspective, and together with the condition that you want equivalence with the subleading soft theorem for the water density of these symmetries, you would conclude that you should allow general diffeomorphisms on the celestial sphere. And in the situations where you can renormalize the charges, this doesn't seem to pose any kind of problem.
Just wanted to add, this structure can also be generalized to higher dimensions, where you also have precisely the shadow transforms very naturally appear.
I guess one of the questions I still have is I'm trying to connect the words I hear and the ideas I hear to the things that I kind of do, where I've got a holographic field theory. And I hear about all these charges that I can measure at scry, and yet in the middle of, you know, a microstate geometry, in the middle of a holographic field theory, I've got an honest to God conformal field theory, and I know the duality, but the operators on that theory. And I'm still suffering from the disconnect between the kinds of things I do and the kinds of things I'm hearing about. And I'm trying to join up the dots. I don't know whether you can help me. That's why I was asking this question earlier about what all these charges turn into when I do the D1, D5 system. Or I don't know whether you can help me, tell me what it is they're telling me about the underlying CFT in that instance.
Maybe I can. It's the right time for me to give my slides on BMS ADS in ADS, because there is a ADS generalization of BMS. Maybe that will help to connect.
Anything.
I think Suvrat also had a comment about that at some point. I think he mentioned something in his discussion, but when he discussed things, but.
So yeah, just maybe, well, and then I go back to your question maybe, but this is just the idea that there is a way to have a structure in ADS which such that its flat limit goes back to BMS. And BMS here, I mean the supertranslations and DFS2. So here, the idea is that to have a BMS structure, you need a foliation and a measure. So in the flat case, the foliation is provided with this foliation of retarded times. And the measure is the measure of the two-dimensional sphere at the boundary, at scry plus. And you can also introduce a structure at the boundary of ADS, or also in the sitter, at the future boundary or past boundary of the sitter. And the way it works is that you simply impose that the boundary metric is boundary gauge fixed. So you can always do it. You choose that your boundary metric as a foliation, and so you put it into that form with du squared, with it's a time-like or space-like, depending if it's the sitter or anti the sitter, and you fix the determinant of the boundary of the metric of the codimension 2 metric QAB. So once you do that, you can always do it because it's just a boundary gauge fixing. So you don't reduce your Cauchy problem. But then the residual symmetries, the residual diffeomorphisms that preserve that, and that preserve some bulk gauge fixing, like Pfefferman-Graham or Bondi, those residual diffeomorphisms form the lambda BMS group. And they admit a good limit when lambda goes to 0, and that's goes back to BMS4. And so maybe a connection with the D1, D5 brain system. Well, if you have an ADS, some open system in ADS, like the near horizon of a brain, and you consider that this brain is inside of some other ADS spacetime, so it can exchange energy. It's not natural to fix the boundary metric because the boundary metric. I mean, you should allow flux to leak in and out of this ADS of this near horizon, and so one way that flux can leak in and out is by changing the boundary metric QAB. And so this kind of more generalized asymptotics and the resulting group lambda BMS is interesting because it gives you a lot of charges that capture this non-conservation and the exchange of energy between your near horizon and the exterior region. And I could just say that you have a well-defined limit. There's some subtleties with corner terms. This is technical, and you can compute surface charge. So all this surface charge algebra and so on. But maybe the main point here is that this is a setup for an ADS with an open boundary, and this is a natural group that appears that capture the charges that are not conserved.
So this would be some kind of response function you could measure. Is that what you're telling me? So yeah, so the associated lambda BMS charges in this case, I mean, they are just part of the stress energy tensor. Good. That obey an evolution equation to you. So if you look at the conserved energy
momentum tensor. Maybe I'll go back to full screen here. So the conserved energy momentum tensor. So it means that it has an evolution along U. So you have a mass and an angular momentum aspect that have an evolution along U. And so those are the two charges that are the lambda BMS charges.
And so this would tell me something about correlation functions of the energy momentum tensor in the conformal field theory.
Right.
Good. Okay, that's very helpful. Thank you.
Can I ask in this context, how do you reproduce the antipodal matching conditions? Like, because there's something special that happens at spatial infinity, which you don't see in ADS because ADS has a smooth boundary. So if I were to impose any sort of boundary condition, nice boundary conditions in ADS, they would all be same angle matching conditions. But somehow when I take the flat limit, then in flat spacetime, in asymptotically flat spacetime, I need to have the boundary conditions have to be antipodal. How does that happen?
It's a good question. I didn't think about it, but somehow my natural answer would be that if you take a retarded foliation and advanced foliation, they will both be a time foliation of the ADS, and so you could do, you could work out the flat limit for both dictionaries, for retarded foliation or an advanced foliation, and just just check that you obtain the same limit in both ways, and that should give you the antipodal map, I would say.
What is the map in ADS? So then you have to also I have to also ask you then, how do the retarded and advanced foliation, the data on the retarded foliation and the data on the advanced foliation should therefore also be antipodally matched? Is that a smooth boundary condition from the ADS point of view?
Yeah, I see what you mean. But I don't.
Maybe let me ask you perhaps a more direct question. What is spatial infinity in ADS? What is the boundary in ADS that maps to spatial infinity? Because there's this whole region in flat spacetime where we impose boundary conditions that no flux can go through. We say that nothing comes in and out of spatial infinity. We have no such boundary in ADS.
Yeah, so I can only see, I can only see scribe plus as a boundary, naturally arising from a limit from ADS, but I don't know how to describe a limit from ADS that could give spatial infinity. That I don't know.
Okay.
Other questions or comments from the audience or the panel?
I think it being 7 o'clock, we should probably wrap it up unless. Yes. Well, I'd like to thank the panelists and Guillaume for refereeing and all of you for participating. And I guess we will pick it up tomorrow at midday with Jose Morales, and he will be speaking about chaos at the rim of the black hole and fuzzball shadows. So if no other questions, we'll call it a night.
See you guys tomorrow.
See you tomorrow, guys. Thank you.